For part one, we're going to talk about the chi-squared one-way goodness of fit test. That little X you see, that's the Greek letter chi, right? It refers to this kind of analysis that we're going to conduct. So what is a goodness of fit test? Well, a goodness of fit test is simply used to evaluate the hypothesis that some observed distribution of counts or frequencies, remember frequencies is just a fancy word for counts, but the idea is that does this observed distribution of counts, does it fit or conform to some claimed distribution about a population? So you have a sample of data and you have an observed distribution from that sample, and you want to test some claim about the population in terms of this distribution of counts. So we use the chi-squared goodness of fit test when we have a table of counts for a categorical variable. And the idea is that we can test whether or not the distribution of this categorical variable is similar to some claimed distribution. So let's look at an example. Let's look at religious affiliation. So suppose a noted religious studies scholar is claiming that young people are just as religious as older generations. So this analysis will focus on people who identify as Protestants, Catholics, and those with no affiliation. So we're looking at a subset of people's religious identities. We're just looking at Protestants, Catholics, and those with no affiliation. But this scholar is claiming that 60% of young people are Protestant, 35% are Catholic, and 5% have no religious affiliation. So this, you could imagine an armchair religious studies scholar just making these claims about the population. And you want to ask, well, this person is just making these claims about the population, claiming that 35% of young people are Catholic, 5% have no religious affiliation. But is that true if we take a random sample from a population and look at the frequencies, if we look at the counts of religious affiliation? So let's test this claim distribution on a data set of Americans aged 18 to 35. So this is a real data set in which we have characteristics of respondents in terms of their age, their gender, and their religion. And then the cases are different respondents. And this is a random sample from people living in the United States. And so the sample size, when we subset, when we look at young people, it's about 518 people. There are 518 rows. So we want to conduct a goodness of fit test using this data. But before we do that, we need to think about some of the requirements. So what are the goodness of fit requirements? Well, there are three main requirements. First of all, the data, they should be randomly selected from a population. Keep in mind, the chi-squared one-way goodness of fit test is an inferential test. It's about trying to make an inference about a population based on a random sample from that population. So we really have to work with random samples from a population. The second main requirement for using this kind of test is that the sample consists of counts for each of the different categories. So we're looking at a distribution of counts. So in the religion example, our distribution will consist of the number of young people who identify as Protestant, Catholic, or have no religious affiliation. And then another requirement is for the inferential test to really work, the expected count should be at least 5 for each of these different categories. So in the religious example, the expected counts for each category should be at least 5. Now the expected count is not the same as the observed count. The expected count is the number of observations that would exist if the data actually have the distribution that is being claimed. So it's possible that your actual data, it might have fewer observed counts than 5 for a particular category. But as long as the expected count is at least 5, we can go ahead and conduct a one-way chi-square goodness of fit test. Really what the expected count test sort of requirement is really saying is that you really need to have a pretty large sample to really conduct this test. And again, of course, there's no requirement that the observed counts for each category must be at least 5. The goodness of fit test has a certain kind of notation. The notation varies somewhat depending on what field of study you're in, but in general, the notation is as follows. We use K to represent the total number of different categories of some categorical variable. So in the religion example, K would equal 3, right? So because we have Protestant, Catholic, and people with no religious affiliation. Those are just the different levels of a factor or different categories of a categorical variable. And then we like to index these number of categories from I equals 1 to K. So in this particular example, in which we talk about young people's religious affiliations, we have I equals 1, I equals 2, and I equals 3, where K is 3. We just like to keep track of these different categories. That's all what's going on. But we like to use capital O with a subscript I, which indexes that particular category, to represent the observed number of counts for a particular category I. So if I equals 1 refers to those young people who are Protestants, O subscript 1 would just be the observed number of counts for a particular category, in which this case it would be Protestants. And then we would like to use capital E with a subscript of I to represent the expected number of counts for a particular category I. So for Protestants, it would be based on whatever the scholar is claiming in terms of the expected number of counts. So the idea behind the goodness of fit test is to really compare these observed versus these expected number of counts. We also like to refer to n. It represents the total sample size. This is lowercase n. Keep in mind, this is because we're working with a random sample from a population. Sample sizes, we typically like to use lowercase n. If we have a population, we like to use capital N. But keep in mind, the reason we're conducting this goodness of fit test is because we don't have a population. We can't, we don't have a population of young people's religious affiliations in the United States. We just have a sample, a random sample. If we had the entire population, we wouldn't even have to conduct the goodness of fit test. We could just look at the population and say, oh, well, the scholar is wrong because, looking at the entire population, using our census data, let's say, we know these observed counts don't conform to what this scholar is claiming. But because we can't have access, we don't have access to people's religious affiliations in the population as a whole, we have to conduct this goodness of fit test. So let's keep going. We like to refer to lowercase p indexed from 1 to k, where k is the number of categories. These are the proportions in the population for the categories. So these values of p, okay, the idea is that they are not observed, okay? They're just like any population proportion. And then we like to use lowercase a, again, indexed for each of the categories. These are the claimed or hypothesized proportion for the categories in the population. This is what the scholar is claiming these proportions are, right? And of course, keep in mind that these proportions, it should be a valid probability distribution. They should add to 1, okay? And you'll see in the religious example that these proportions do in fact equal 1. To put another way, these probabilities equal to 1. Because when we talked about probability, remember that we can treat proportions as probabilities in certain instances. So let's look at this religious affiliation example using this notation. So this is just a basic table of counts for our religious affiliation variable. You can see that we have 247 young people who identify as Protestant, 132 who identify as Catholic, and 139 who don't have any kind of religious affiliation. So this is just a basic table of counts, a frequency table. And we can see that there are 3 categories. So we're going to refer to category 1 as Protestant, category 2 as Catholic, and category 3 as none. And k equals 3 because there are 3 categories. And the total sample size is roughly above 500. Now for each of these categories, we have observed counts. Those are simply the values from the frequency table. So we can see that for the Protestant group, we have about 247 Protestants. O subscript 2 refers to 132 Catholics, and O subscript 3 refers to 139 young people who don't have religious affiliation. And then we have these claimed proportions. These are from the religious studies scholar. Okay? This is the armchair philosophizer just kind of sitting in his armchair saying, well, 60% of young people are Protestant, 35% are Catholic, 5% are none. What we're trying to do is, based on these claimed proportions, we're trying to see, well, how does this compare to the actual data? These claimed proportions, they should equal to 1. That's because we can interpret these proportions as probabilities. The probability, according to this religious studies scholar, of a young person being Protestant is 0.6. This religious studies scholar is claiming that the probability of a young person being Catholic is 0.35, and the probability of a young person being having no religious affiliation is about 0.05. So let's continue on with a religious study example. The crux, the key part of the chi-square one-way goodness of fit test revolves around the expected cell counts. So we must count the number of expected cell counts. So the expected cell counts are simply E subscript I equals N, which is the total sample size from our data, times A subscript I, where A just refers to the claimed proportion in the population. So recall that this scholar is saying these proportions are 0.60, 0.35, and 0.05, respectively, for Protestant, Catholic, and young people without a religious affiliation. So the sample size is above 500. So to calculate the expected cell counts based on this distribution, this claimed distribution in the population by this religious studies scholar, we just multiply the total sample size by the proportion. Okay? So if we multiply 518 times 0.60, 0.60 is the claimed proportion in the population by the religious studies scholar. If that religious studies scholar is correct, using this sample of data, we'd expect about 310 young people to be Protestant. Right? According to the religious studies scholar, we'd expect about 181 young people to be Catholic. And according to the religious studies scholar, if his distribution in the population is correct, we would expect about 26, roughly, young people to have no religious affiliation. So these are the expected counts. And the goal is to compare these expected cell counts with the observed cell counts in our data. So this is all the sort of information we need to really conduct the chi-square one-way goodness of fit test.